Okay, see, just I wanted to explain this once again. Okay, actually, the heat conduction equation in Cartesian coordinates. Okay, so in the last class we discussed about this. Qs is nothing but the heat entering the solid, and Qx plus dx is the heat which leaves the solid. Okay, and when we know that if heat energy is conducted by a body, there will be some change in internal energy, or from first law of thermodynamics, we know that Q minus W, which is equal to del U. Am I correct or not? Am I correct?
Yes, sir.
Okay. So in the last class, we discussed about this. Okay, Qx and the heat entering the control volume, or the heat entering the rectangular parallel piped solid as Qx, and the heat which leaves is Qx plus dx. Okay, similarly along the y-axis Qy and Qy plus dy, and in along the z-axis Qz and z plus dz respectively. Okay, entering and leaving is x and x plus dx. Similarly, y plus dy, and z plus dz. Okay, and yeah, let T be the temperature at the left side.
So,
Yeah, hello.
are you sharing the screen because it's not visible?
Oh, I'm sorry, I'm sorry. I you. Sorry. I don't know why my system has become that much slow. Yeah, I think is it visible now, right?
Yes, sir.
Yes,
No.
sir.
Yes, sir.
So, yeah, I'm sorry. Actually, you people, you didn't see it. So this is the rectangular parallel pipe where you have this that is the solid. Okay, and along the x-axis Qx is the heat energy which enters the solid, and Qx plus dx is the heat energy heat which is conducted out of the solid. Similarly, along the y-axis Qy and uh, the heat energy leaving the solid along the y-axis is Qy plus dy, and similarly in the z-axis Qz, and Qz plus dz is the energy which conducted out of the solid. Okay, so along all the three axes, okay, x, y, and z. Okay, and we also know that capital Qg, which is equal to Qg into um, dx, dy, and dz, where dx, dy, and dz is nothing but the volume, and this q suffix g is nothing but the heat generated. Okay, so that also you should know, internal heat generated. Okay, so qx has nothing but the heat conducted, or heat conducted along the x-axis, y-axis, and z-axis is given by qy and qz, and qg is nothing but the internal heat generated. Okay. Now let T be the temperature, and dt by dx be the temperature changes, and along the x-axis, and the rate of change along the x-axis or x-axis direction. Okay, and small qg is nothing but the heat generated per unit volume per unit time. Okay, and we know that the heat flux is, okay, minus k into a into dt by dx into dou t, and uh, we know that since it is heat flux, okay, the area will be yeah, it will be in watt per the area will be in meter squared, and heat flux will be in watt per meter squared. Okay, so and similarly it was mentioned as heat flux along x plus dx is qx dash plus dou by dou x of qx dash into dx. Okay, and you can substitute this value of qx dash here, and similarly here. Okay, when you substitute the qx dash value, the equation becomes qx dash minus minus of qx dash plus dou. Oh, sorry, I'm sorry. You can substitute the qx dash value here. Okay, in these two places you can substitute, and heat accumulation, net heat accumulation in the element due to heat flow in direction will be the first one, this one qx dash minus q dash of x plus dx. Okay, so that's what it was mentioned. Okay, dqx dash is qx dash minus this one. Okay, qx dash plus dou by dou x of qx dash into dx. Okay, so that's what it was mentioned here. Okay, net heat accumulated along the x-axis direction. So when you substitute this, okay, you will be getting see, we know that qx dash and qx dash gets cancelled, so this minus sign enters inside, so minus of dou by dou x of qx dash into dx, and substituting qx dash here, we know that qx dash is minus kx into dy dx dou t by dou x into dou t. So when you substitute it here, you will be getting dou by dou x of kx into dou t by dou x into dx dy dz dou t. And similarly, we will be getting the expression for dqy dash and dqz dash. Okay, or in other words, heat accumulation along the y-axis and z-axis, you will be getting this expression. Okay, and when you include this dou by dou x inside, then what happens here is dou square t by dou x squared into kx into dx dy dz dt. Okay, and when you include this dou by dou y inside, ky into dou square t by dou y squared, and when you include this dou by dou z inside, then kz into dou square t by dou z square. Okay, am I correct or not? Dou square t by dou x squared, dou square t by dou y squared, dou square t by dou z squared. Am I correct? When you include this, multiply this with this,
Yes, sir.
so the equation will be of this form. And similarly, we also know that the energy stored in the element is um, rho into volume. Okay, rho into volume into C into dou T by dou T. Or in other words, the energy stored in the elements or heat energy in the body is mass into specific heat capacity into rise in temperature. Now, we know that what is density? Density is mass by volume. Am I correct? Density is mass by volume. Am I correct or not?
Sir.
Yes,
So,
yes, sir.
mass which is equal to density into volume. We can write that like that also. Am I correct?
Yes.
What here?
Yes, sir.
Am I correct or not?
Yes, sir. Correct, sir.
Density equal to mass by volume, m by v. Rho equal to m by v, or m equal to rho into v. Am I correct?
Yes, sir.
Okay, so the rho is nothing but the density here, and dx, dy, and dz is nothing but the volume here. Okay, when you take the volume of the solid, dx, dz, and dy. Am I correct? The volume in meter cube. So what happens here is the energy stored in the element, instead of putting here as mass, they have put density into volume into specific capacity into rise in temperature of the body. Okay, now we know that the net heat accumulated plus internal heat generated, which is equal to energy stored. Okay, so that's what the energy balance says us. Okay, net heat accumulated plus internal heat generated due to the heat flow, which is equal to the energy stored at a given time. Okay, and now what happens here is we can all in all the three terms we have dx, dy, and dz. Okay, dx, dy, dz, dx, dy, dz in all the three terms. Okay, on the left hand side we have two terms which involves dx, dy, and dz. Similarly, and the right hand side also. So we have the liberty to divide everything with respect that is by dx, dy, dz, and dt. Okay, so when you divide it, we will be getting the expression dou by dou x of kx into dou t by dou x, and let us include this dou by dou x inside. So kx into dou square t by dou x squared, ky plus ky into dou square t by dou y squared plus kz into dou square t by dou z square plus qg, which is equal to rho into c into dou t by dou t. Okay, so this is the final expression. Okay, and when we use the vector, we will be getting this equation like this. Okay, so this is said to be the general conduction equation, dou square t by dou x squared. Yeah, Now there is one more thing which I want to tell you. Now you have this kx, ky, and kz. Okay, so there is one material which is said to be isotropic material, which will be having same thermal conductivity in all the three directions, x-axis, y-axis, and z-axis. By assuming the material which we consider as isotropic material, we are we have the liberty to say kx equal to ky equal to kz. Okay, but in practical cases, some of the researchers, they say it is not constant, but we assume constant thermal conductivity value for all the materials, but it also differs by direction. Okay, by assuming isotropic material, we will be having we assume the thermal conductivity to be same in all the three directions. Okay, so we can rewrite this kx, ky, and kz as k. Okay, since kx equal to ky equal to kz, and the material as the material which is having constant thermal conductivity in all the three directions. Okay, so assuming constant thermal conductivity, kx equal to ky equal to kz equal to k. Now the equation becomes dou square t by dou x squared plus dou square t by dou s squared plus dou square t by dou z squared plus qg by k, which is equal to rho c by k. Now this rho c by k is nothing but the inverse of thermal diffusivity. Okay, 1 by alpha. Alpha is nothing but k by rho c. Okay, thermal conductivity divided by thermal capacity. Okay, thermal conductivity, it is the ratio. Thermal diffusivity is nothing but the ratio which is equal to the it is the ratio of thermal conductivity to thermal capacity. And one of the important advantage, or one of the important thing why we have to discuss about thermal diffusivity, because it gives us an idea about how faster the heat is transferred from inside the material. Okay, how it easily diffuses inside, how the heat easily diffuses inside the material. Okay, so that's the advantage in finding out the thermal diffusivity. And what we have is uh, we can rewrite this equation as by using Laplacian function. Okay, del square t plus qg by k, which is equal to 1 by alpha dou t by dou t. And for if there is no internal heat generation, then what happens to the term is this qg by k becomes 0. Then the equation becomes Fourier equation. And similarly, what happens is when it is steady state condition, then this equation becomes Poisson equation. Okay, del square t plus qg by k equal to 0. So if there is no internal heat generation, then del square t which is equal to 1 by alpha by dou t by dou t. So the equation becomes Fourier equation. If it is steady state, means then the right hand side becomes 0. Then del square t plus qg by k equal to 0. Then the equation becomes Poisson equation. And finally, if there is no internal heat generation and if there is steady state, then it becomes the equation becomes dou square t by dou x squared plus dou square t by dou s squared plus dou square t by dou z squared, which is equal to 0. Laplace equation. Okay, so these three things you should know. Okay, so the basic mathematical thing knowledge you should have. Okay, so the general equation is, this is the general equation. Okay, dou square t by dou s squared plus dou square t by dou s squared plus dou square t by dou z squared, which takes care of all the three directions, x, y, and z. And plus qg by k. Qg by k is nothing but it takes care of the internal heat generation. Okay, and on the right hand side, it is nothing but the stored energy. Okay, I already told you the energy stored is calculated in the term mcp del t. Okay, yeah, mass. So the mass is substituted in as density into volume. We know that density equal to mass by volume. So density into volume they have substituted. Specific capacity is capital C, and rise in temperature is dou T by dou T. Okay, and you should also know about the thermal diffusivity, which is again one more property which gives us an idea about how faster the heat gets transferred within the body, within the material. Okay, so the thermal diffusivity depends upon the thermal conductivity as well as the density and specific heat capacity of the particular solid. Okay, particular material you consider. Okay, so thermal diffusivity, it's also very important. That's why water is always used. Okay, in case of steam power plants and nuclear reactors, water is used as a coolant. Okay, we know that the conductivity of water is lesser, but the storage capacity, okay, the storage capacity of energy storage capacity of water is higher. Okay, water can store more heat energy. Okay, so these things you should know. Okay, and what happens is for one dimensional steady state heat transfer with internal heat generation, okay, and the equation becomes dou square T by dou x square plus qg by k. For steady state one dimensional without internal heat generation, see, for one dimensional means we have to neglect the y-axis and z-axis. We should consider only x-axis. So dou square T by dou x squared plus qg by k, which is equal to 0. And similarly, for without internal heat generation means then the equation becomes dou square T by dou x squared, which is equal to 0. From this only we got the expression in the last class. I don't know how many of you seen it, or I derived one expression. Am I correct? We have derived this T1 minus T2 divided by L by Ka. All of you are able to see this?
Yes, sir.
Yes, sir.
See, dou square T by dou x squared equal to 0. When we double integrate it, we will be getting the C1x and C2. And when we apply the boundary conditions at x equal to 0, t equal to T1, when you substitute this in the equation at x equal to 0, t equal to T1. So C1, this term becomes 0, C2 equal to T1. So we will be getting C2 equal to T1. And when you substitute x equal to L, then what happens here is C1 into L plus T2 will be equal to T1 C1 into x C1 into L plus T1, which is equal to T2. So you can see here T2 equal to C1 into L plus C2, and finding out C1 from this, we will be getting T2 minus T1 by L. So substituting the constant C1 and C2 in the equation, we will be getting the solution as temperature, which is a function of x. Okay, so T2 minus T1 divided by T2 minus T1 divided by L into x plus T1. Okay, so this is the final solution. And we also know that Qx, the heat conductor in the x-axis is minus Ka dt by dx, and Ka by L, which is equal to Ka by L into T1 minus T2, or it is also rewritten as T1 minus T2 by L by Ka, where L by Ka is nothing but the thermal resistance. Okay, so just like electrical resistance, thermal conductive resistance is given by L by Ka, and its unit is in Kelvin by watt. Okay, so the resistances. Now, suppose if we have two liquids are having two different thermal conductivity, one on the left hand side and the other on the right hand side, that the convective heat transfer coefficient of the liquid which is there, or a fluid, don't say liquid, of the fluid where on the left hand side is H1, and convective heat transfer coefficient of the fluid on the other side uh, uh, BH2, then what happens is instead of one single resistance like this, we will be having three resistances. The three resistances mainly due to the convective heat transfer coefficient of the first side, and the thermal conductivity resistance and convective resistance on the second side. Okay, now we will be having the thermal circuit like this. So you will be having three resistances. First one is convective resistance, second one is conductive resistance, and the third one is convective resistance. That is mainly due to the two different fluids on both the sides. For example, practical example, let me say water tank. Okay, so suppose water tank, inside the tank you will be having water. Am I correct? Inside the tank you will be having the water, and outside you will be having air. Am I correct or not?
Yes, sir.
If you take example of water tank, in our houses we have the water tank. Okay, so now what happens is the convective heat transfer coefficient of water, okay, will be higher when compared to the convective heat transfer coefficient of the air. Am I correct or not? We have seen in the previous slides. Okay, water and air, free convection. For gases it is 2 to 25, for liquids it is 50 to 100, and definitely air is having lesser and water is having higher. Okay, so the convective heat transfer coefficient of the hot fluid will be higher, and the convective heat transfer coefficient of the air will be lower. Okay, so now if you have in between, you will be having the wall. Okay, the solid wall which is made of brick or which is made of uh, uh, the different material. And nowadays we have the tanks, okay, which is made of composite material which consists of bakelite and other materials. Okay, so when we talk about this, what happens is we will be having three resistances. Am I correct or not? First, inside fuel fluid, assuming water is the inner fluid, it will be having one convective heat transfer coefficient, and outside fluid air, which will be having other convective heat transfer coefficient, and we will be having thermal conductivity of the material, which leads to thermal resistance, conductive resistance. Okay, so 1 by H1 into A is convective resistance, L by K is conductive resistance, and 1 by H2 A is convective resistance again. So when you have two different fluids, one on the inner side and the other one of on outer side, then you will be having the heat conducted through the through the solid from one higher side, from one side to other side, is like this. All of you are able to understand,
Yes, sir.
students? And you will be having three resistances. You will not only having the conductive resistance alone. Okay, you will be having a combo of conductive resistance and convective resistance. Is it fine, students? Is it fine?
Yes, sir.
Yes,
Okay.
sir.
Now in this case, what happens is we will not be see, since it involves both conductive resistance as well as convective resistance, we will be having a combo of our we usually we used to write like this: the heat flux is equal to T1 minus T2 divided by summation of all the resistances. Why it is so? Because the heat convected, or the total heat conducted from inner fluid to the outer fluid, is T1 minus T infinity 1 minus T1 divided by 1 by H1 into A, and then T1 minus T2 by L by Ka, which is equal to T2 minus T infinity by 1 by H2A. Okay, or when we add all these things, it becomes T1 minus T2, or sorry, T infinity 1 minus T infinity 2 divided by summation of, or summation of all the resistances. Okay, 1 by Ha, L by Ka, and 1 by H2A. Okay, now instead of denoting this as all the resistances, we used to have one coefficient known as overall heat transfer coefficient. Okay, normally all the practical devices we have, it will be having a combination of convection and conductive resistances. I have told you about the car radiator, right? Car radiator, engine cylinder, everything. Okay, so it will be having a combination of conductive and convective resistances. So instead of saying conductive resistance and convective resistance, and saying heat transfer coefficient of inside and heat transfer coefficient outside, generally we used to have the term overall heat transfer coefficient, which is denoted as capital U, which is denoted by capital U. This capital UA is nothing but 1 by R total, that is 1 by H1 plus L by K plus 1 by H2, and it the units of this UA is watt per Kelvin, and we know that thermal resistance is given by Kelvin by watt. Okay, so we used to have this term in normal devices. We used to have the term overall heat transfer coefficient, Q equal to UA del T, where UA is nothing but 1 by R total. Okay, 1 by a summation of all the resistances which involves convection as well as conduction is equal to UA. Okay, so Q equal to UA del T, or del T divided by R total, whereas UA is equal to 1 by R total. So generally we will be using the term overall heat transfer coefficient. Okay, we will not be using the using this term. Okay, convective resistance inside, convective resistance outside, and then conductive resistance. Okay, instead of that, we will be using the term overall heat transfer coefficient, which is given by capital U. Is it fine, students? Is it fine?
Yes, sir.
Yes, sir.
Okay. And before going on to the composite wall, let me solve one problem, because we were teaching so much theory, right? So let us solve only one problem. Okay. All of you please take down this, or let me copy it down, and you can yeah. Today I will just upload this problems in Moodle. Sorry, not Moodle, in MS Teams. Okay. This PPT itself I will upload, so that it will be easier for you to understand. You can start practicing, because inside the classroom it's very difficult for us to solve each and every problem. I will be solving 1 or 2 problems. That's what I will be giving you as assignments. Is it visible?
Yes, sir.
Sir.
Is it visible to everyone?
Yes, sir.
Okay. Now, just now in the previous case I have told you, you have a solid, and on the inner side you have one fluid, and on the other side you will be having other fluid. Okay, the same example is here. A mild steel tank of wall thickness 12 mm contains water at 95 degrees C. All of you can take it down. So while I solve the problem, all of you please take it down. So a mild steel tank of wall thickness 12 mm contains water at 95 degrees C. The temperature, the thermal conductivity of steel is 50 watt per meter Kelvin. The heat transfer coefficient inside is 2850 and outside is 10. Okay, if the atmospheric temperature is 15 degrees C, calculate the rate of heat loss per meter squared of the tank, and the temperature at the inner side and outer side of the tank. Okay, so this is what it was mentioned. Okay, so all of you please take this problem, okay, in your notebook. Let me draw the small diagram and circuit so that it is easier for you to understand. Yeah, is it visible, ma?
Yes, sir.
Yes, sir.
Now it was mentioned here a mild steel tank, and it is of having thickness. Okay, now assume the thickness as 12 mm. Okay, and inside you will be having water. Let the temperature of water as T suffix A, T suffix A as 95 degrees C, and temperature of air, outside air you will be having air will be circulating, so T suffix B as 15 degrees C. Okay, now it's going to be the temperature difference. So when you substitute in Kelvin or degree C, the temperature difference will be the same. Okay, for example, 273 plus 95, 368, and here it is 288. Okay, so the difference 368 minus 288, the difference is going to be 80. Okay, when you substitute the values in degrees C also, the temperature difference is going to be 80. So now you have this HEA, which is equal to 2850 watt per. All of you please take down the problem, watt per meter squared Kelvin, and H suffix B, which is equal to 10 watt per meter squared Kelvin. Okay, now what is we know that the law of thermodynamics, heat transfer will be taking place from the high temperature body towards the low temperature body. Now water is at a higher temperature, the heat is transferred from the water to the inner side. Inner temperature is T1, outer surface is T2. So the heat transfer direction, and then it is so the heat is transferred like this. Or when we draw the thermal circuit, we will be having convective resistance, and then we will be having conductive resistance. And who is that? Please mute yourself. Newman.
Sir, sorry, sir.
Yeah. So you will be having the combination of 3 resistances. Okay. So you will be having temperature TA, and then T1, T2, and then T suffix B. Am I correct, students? The circuit I have drawn is correct or not? Students, is it correct?
Yes, sir. Yes, sir.
So this is the first resistance, thermal conductive resistance or convective, and this is or conductive, and again this is or convective. Okay, why I say or convective, or conductive, and or convective? Three resistances. The first resistance is offered by the fluid, and second resistance is offered by the solid, and the third resistance is offered by the air. Okay, so HA and HP were given, and thermal conductivity. The thermal conductivity of steel is mentioned as 50 watt per meter Kelvin. Sometimes if it will not be given, the thermal conductivity will not be given in the problem. Okay, so if thermal conductivity is not given, and if you are asked to find out the heat transfer coefficient, heat loss per meter squared of the tank, okay, then you have to take the value of thermal conductivity from the heat and mass transfer data book. Okay, so the heat transfer data book will be having all the conductivity properties of all the materials. Okay, so if it is given as copper or aluminum, then in the question itself you can you will be mentioned take data from heat transfer data book. Okay, if nothing is mentioned, then you have to, as design engineers, you have to take the values from the heat transfer data book. Okay, now we know that Q equal to, what is convective resistance, or convective is equal to 1 by HA into A on the left hand side. Okay, so take it as R convective 1, this is R convective 2, and R conductive is equal to, kindly bear with me because I am writing on a very smooth surface, so the handwriting will not be that much great. L1 by K1 into A. Okay, and all of you have taken the problem, all of you?
Yes,
Yes.
sir.
Yes,
Yes,
sir.
sir.
And R convective 2, R convective 2, the third resistance is 1 by HB into A. Now, in the question itself, it was mentioned that you are assumed to calculate the heat loss per meter squared of area. So, assuming area as 1 meter squared or per meter squared area, you are expected to calculate. Now, what happens here is, then Q will be equal to del T by sigma R, summation of all the resistances. Now del T is TA minus TB divided by 1 by HA into A. What is 1 by HA? HA value
So 2850.
2850. 1 by 2850 plus the, what is the other value? L1 by K1 into A1. The distance is only 12 mm. Okay, substitute 12 mm in meters. 12 into 10 power minus 3. Okay, 12 mm. It is 12 mm. So always substitute in meters. Generally the students will be doing the mistake here. So 0.012 divided by K value 50. Am I correct? Thermal conductivity.
Yes, sir.
The thermal conductivity is given as 50. So K1, which is equal to 50. Okay, now plus 1 by HB into A. What is thermal conductivity of the other side? 10 watt per meter squared Kelvin. So plus 1 by 10. Okay, now TA minus TB. TA minus TB is, substituting TA minus TB as how much it is? 95 minus 15. Am I correct?
Yes, sir.
Okay, that is TA minus TB. So you can just rub it off also. So find out Q. It will be in watt per meter squared. How much it is? 80 divided by these values. Calculators. 0.012 ma. This is 2. Students, all of you are able to understand how I did this?
Yes, sir.
Yes, sir.
What is the value? A mild steel tank of wall thickness 12 mm contains water at 95 degrees C. The thermal conductivity of mild steel is 50 watt per meter Kelvin, and inside and outside coefficient is 2850 and 10. Outside temperature is 15. So calculate the heat loss and interface temperatures. Yeah, how much it is?
795.3.
795.3. Is it correct, students?
Yes, sir. Even I'm getting the same value.
Okay, ma. Now,
Yes, sir.
they are asking us to find the interface temperature also. Now, to get the interface temperature, you have to take resistances one by one. Now, the overall heat transferred is 795.19. How much you said? 795.3. I'm sorry. 795.3. Now, to find out this temperature T1 and T2 intermediate temperatures, you have to take the one particular direction. So, sorry, one particular resistance. Okay. So, Q equal to 795.3. Q equal to 795.3. Taking the first resistance alone, which is equal to TA minus T1 divided by 1 by HA into A. Okay, so TA we know that 95 minus T1 divided by 1 by 2850. Okay, now from this equation find out what is T1. Find out T1.
Sir.
Yeah.
Sir, but shouldn't we convert degrees Celsius to Kelvin, or is it not necessary? Sir?
No, the temperature, the difference is going to be the same. When you say 100 degrees C minus 0 degrees C, it is equal to 100. 373 Kelvin minus 273 Kelvin is equal to 100. Okay.
Right, yeah, got it.
Yeah, the temperature difference anyway, it's going to be the same. How much it is T1?
Sir, I'm getting 94.72, sir.
Yeah, that is correct. 94.72. T1, which is equal to 94.72 degrees C. And try to find out T2 also. Now, use the second resistance. Okay, now we have got T1. Okay, so T1 minus Q equal to, again, let me write like this. Let me rub off this. Q equal to 795.3 Dhanama. Am I correct? It's not 5.
Yes, sir. Yes, sir.
Yes, sir, 3 only.
Okay, which is equal to T1 minus T2 by the conductive resistance or conductive. So T1 minus T2 divided by L1 by K1 into A1. So now we know that 795.3, which is equal to T1. Now we got it as 95.7, 94.7. So 94.7 minus T2 divided by L1, 0.012 divided by K. What is K value? Thermal conductivity 50, yeah? Yeah, 50. Okay, so when you substitute this, you will be getting T2, intermediate temperature. 795.3, which is equal to 94.7 minus T2 divided by 0.02 by 0.12 by 50. How much it is?
94.53.
94.53. So from this we can see that 94.7 is the inner temperature and 94.53 is the outer temperature. So what it shows us, since the material has got higher thermal conductivity, similarly the thickness of the material is also lesser. 94 point, how much you said, ma?
53.
5 3.
5 degrees C. Okay, so this is T2 and the other one is T1. 94.72. Since the material has got a higher thermal conductivity, suppose if you select a lesser thermal conductivity material, then what happens is the heat transfer will not be that much great. Okay, so that's why I told you in case of refrigerator walls, we will be having sheet metal, and it is a composite wall where inner we will be having asbestos like insulator, so that the outside heat will not be passing inside. Okay, the outside heat will not be passing inside, so that the inner material will be chill. When we just open the refrigerator also, we feel it, we can feel it. Okay, so any doubt in this, how to solve this problem? This is a very small problem which I did. Complicated problems we have to solve. Okay, any doubt? All of you have taken this?
Yes, sir.
See, I didn't substitute area because you are asked to find out the rate of heat loss per meter squared of the tank. All of you have taken this problem. What I will do is I will just upload this PPT in MS Teams. Okay, so the second problem is also like the same thing, ma. Okay, please do this problem. Okay, second problem is very similar to the first one. Okay, so second problem is very similar to the first one. 100 degrees of vapor on one side and cooling water 25 degrees on the other side. Only 4 mm thickness plate, and then thermal conductivity is 95.5. Heat transfer coefficient, vapor side is given, water side is given. Calculate just a similar problem. Okay, just the same problem. Can you do this? Let me put both the problems in the chat box itself now itself. So my request to you people is, you have to those who solved the first problem today, you are expected to give me the solution tomorrow. Okay, because each and every problem, if I do it now, it will be wastage of time, as well as the same principle. Okay, has it come in the chat box?
Yes, sir. Visible, sir.
Okay, ma.
Yes, sir.
So please take down the second question also, right? Please take down the second question also. Try to solve it. Okay, because tomorrow I will be moving on to the composite problem, composite wall problem. Okay, so please, both the problems are visible, right, in the chat box? Yes. All of you please check.
Yes,
Yes,
sir.
sir.
Okay, so the second problem is just like the previous first problem. Okay, the second problem is only differences, the plate thicknesses varies, and the heat transfer coefficient values varies. One side it is vapor and the other side is water. Just like the first problem, you have to solve. Is it fine? Whether you will be able to solve?
Yes, sir.
Okay, try to solve more number of problems. Ma. With this, I stop this recording, and on Thursday we will meet by 8:55. Am I correct?
Yes, sir.
Yeah, let me download the attendance. So especially how we get the Poisson equation, how we get the Laplace equation, Fourier equation, and all, it's very important, ma. So try to go through the textbooks. Okay, so that's why I have given you 3 textbooks. Okay, so try to go through the textbooks also. Okay, and try to solve more numericals, especially in Rajput we have so many numericals, and I have taken some problems from Rajput only. Okay, especially the first problem or second problem I have taken from Rajput only. Try to go through it and try to solve it. Okay, is it fine?
Yes, sir.
Okay, ma. And if you don't have any questions, you can start leaving.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, Ma.
Thank
Please
you,
join
sir.
by 8:55 on Thursday. Please join by 8:55 on Thursday.
Thank you, sir.
Thank you. Thank you.
Thank
You
you,
can
sir.
leave, Ma. You
Thank
can
you,
leave.
sir.
Thank you. Manish, do you want to? Ranjit,